Alright, let's dive straight into the fascinating world of robot kinematics. We're looking at how a simple two-joint robot arm moves its end effector, that's the gripper or tool at the end, around in space. This diagram shows the basic setup. Two links, L1 and L2, connected by joints that can rotate by angles θ1 and θ2. The goal is to figure out exactly where the tip of the arm, point X, Y, is located based on these angles. So, how do we get from those joint angles θ1 and θ2 to the actual position X, Y? It's all about vector addition. Think of each link as a vector. The first link contributes a vector based on its length L1 and angle θ1. The second link contributes another vector based on its length L2 and the combined angle θ1 plus θ2. Add them up, and boom, you get the position of the end effector. Now, what if we want to know how fast the end effector is moving? That's where the Jacobian matrix comes in. It's like a translator between the world of joint velocities, how fast the joints are turning, and the world of end effector velocities, how fast the tip is moving. The equation x dot equals j times θ dot tells us this relationship. If you know the joint speeds θ dot, the Jacobian j tells you the resulting end effector speed x dot. It maps the robot's internal state, joint space, to its external action, end effector space. Now, let's talk about the velocity ellipsoid. Imagine you fix the robot's configuration, so the Jacobian matrix j is fixed. What kind of end effector velocities can the robot achieve? Well, it turns out they form an ellipsoid shape in velocity space. Think of it like this. Depending on the robot's current pose, it might be able to move quickly in one direction but very slowly in another. The shape of this ellipsoid tells you the robot's capabilities in terms of speed and direction at that specific moment. It's a crucial concept for understanding the robot's performance limits and planning efficient movements. Let's look at a simpler example, a 1R robot, meaning one revolute joint. Here, the end effector position P is defined by polar coordinates r and θ. Converting this to Cartesian coordinates gives us the familiar equations for x and y. Now, what about velocity? If the joint rotates with angular velocity θ dot, the end effector velocity components x dot and y dot depend on both r and θ. Notice how the velocity isn't just radial, it has tangential components too. This is captured neatly in the matrix form shown, where the Jacobian matrix directly relates the single joint velocity θ dot to the two-dimensional end effector velocity x dot, y dot. This simple case already illustrates the core principle. Okay, let's crank up the complexity. A3R planar manipulator. 3 joints, 3 links. We need to find the position of the end effector P. This involves using transformation matrices. Each joint introduces a rotation and potentially a translation. We build the overall transformation from the base frame to the tool frame by multiplying these individual transformations. The final matrix T toolbase gives us the position and orientation of the end effector. To find the velocity, we differentiate this transformation with respect to time, which involves calculating the derivatives of the rotation and translation components. The resulting matrix equation shows how the end effector velocity is related to the joint velocities θ1 dot, θ2 dot, θ3 dot through the Jacobian matrix. Notice the structure. The first 3 rows relate linear velocity, the last 3 relate angular velocity. Now we're talking about a SCARA robot, a common type used in assembly lines. It's a 4-axis robot, typically with 2 rotational axes for the horizontal plane, 1 vertical axis for the elbow, and sometimes a 4th axis for the wrist. Look at the diagram, it shows the typical structure. We need to define the coordinate frames for each link, starting from the base. This is crucial for applying the Denevit-Hartenberg convention, which we'll touch upon later. The goal is to find the position of the end effector P. Again, we use transformation matrices. For SCARA, we often consider the vertical motion as a prismatic joint, so we have a mix of rotations and translations. The complexity increases, but the fundamental principle remains: chain the transformations together. For the SCARA robot, the transformation from the tool frame to the base frame, T sub toolbase of Q, gets more involved. We need to account for the rotations of the first 2 joints, θ1, θ2, the vertical translation, Q3, which is d3 in the diagram, and the rotation of the wrist, theta 4. The formula breaks down these transformations into manageable parts. Notice how the exponential function exp of q4 divided by pi appears. This is often used to handle the wrist rotation smoothly, especially when dealing with singularities. The vector w of q represents the position and orientation of the end effector. The terms w1 through w6 are derived from the geometry and joint angles, showing how the end effector's position and orientation change with the robot's configuration. Continuing with the scala, let's look at the vector w of q again. It explicitly shows how the end effector position px, py, pz, and orientation, represented by w4, w5, w6, depend on the joint variables q1, q2, q3, q4. The first three components give the position, the last three give the orientation. Now, the Jacobian. This is the 6x4 matrix J of Q. It's a bit bigger than the 2R case because we're dealing with 6D space, 3D position, 3D orientation, and 4 joint variables. The structure is similar. The top 3x4 part relates linear velocities to joint velocities, and the bottom 3x4 part relates angular velocities to joint velocities. Calculating this Jacobian requires careful differentiation of the elements of W of Q with respect to each joint variable Qi. This matrix is key for controlling the scala robot's motion. Let's step up to a 5-axis articulated robot, like the Rhino XR3. This is more complex, with multiple rotational joints allowing for greater flexibility in positioning and orienting the end effector. The diagram shows the typical joint structure. Again, we'd use transformation matrices, likely employing the Denevit-Hartenberg parameters to systematically define the frames. The vector psi of q here represents the end effector pose, including position and orientation, but the exact form depends on the specific robot's geometry and joint types. The complexity of the Jacobian matrix will also increase significantly, becoming a 6x5 matrix. Analyzing these higher degree of freedom robots requires robust mathematical tools and computational power. Now, let's talk about something called singularity. What happens when a robot reaches a singularity? It's like hitting a wall, but not physically. It's a configuration where the robot loses its ability to move in certain directions. Think of a human arm. If you stretch your arm straight out, you can't bend your wrist independently anymore. The robot's Jacobian matrix J tells us about this. Remember, x dot equals J times theta dot. If the robot is at a singularity, the Jacobian matrix becomes singular, meaning its determinant is 0. This means the matrix is not invertible. If we want to find the required joint velocities theta dot to achieve a desired end effector velocity x dot, we'd normally use theta dot equals J inverse times x dot. But if J is singular, J inverse doesn't exist. So, the robot can't achieve every possible end effector velocity. It's blocked in certain directions. How do we find these problematic configurations? We look for when the determinant of the Jacobian matrix is 0. Here's how we mathematically find those singularity points. We take the Jacobian matrix J for our robot, for example, the 2R robot we saw earlier. We calculate its determinant. The determinant of a matrix is a scalar value that tells us about the matrix's properties. If the determinant is 0, the matrix is singular. So, we set the determinant of the Jacobian equal to 0 and solve for the joint angles theta 1 and theta 2. The solutions to this equation represent the robot's singular configurations. In the example shown, the calculation leads to a condition where the product of the lengths L1 and L2 must be 0, which is a structural singularity for this specific two-link arm. Finding these singularities is crucial for avoiding them during robot operation and path planning. Alright, we've covered the basics of how robots move, their kinematics. Now, let's shift gears to trajectory planning. Knowing where the robot can go is one thing, but figuring out how to get there smoothly and efficiently is another. This is where trajectory planning comes in. So, Unit 3 is all about trajectory planning. We're going to explore how to define the path a robot takes over time, not just the start and end points, but the entire journey in between. When we talk about controlling a robot's path, there are different modes, Think of point-to-point control, PTP. It's like telling the robot, go from here to there. The robot figures out the quickest way to get there, but the path it takes in between isn't necessarily controlled. It's great for pick-and-place tasks. Then there's continuous path control, CP. This is more precise. You tell the robot, follow this exact path, maintaining this speed and orientation. This is essential for tasks like painting, welding, or cutting, where the quality depends on the smoothness of the motion. Let's break down PTP and CP. Point to point is simple. The robot just needs to get from point A to point B, C, D, etc. The path it takes is secondary. It's fast and efficient for tasks like grabbing a box and putting it somewhere else. The downside is, if you need the robot to follow a specific contour, PTP won't work. Continuous path, on the other hand, is all about the journey. The robot must follow the specified path precisely. Think of a robot arm painting a car door. It needs to stay perfectly parallel to the surface. This requires more sophisticated control and programming, but it's essential for high-quality applications. Choosing the right mode depends entirely on the task. Within continuous path control, we have specific techniques. Linear interpolation is the most common. The robot moves in a straight line between 2 points. Simple, effective for many tasks. Circular interpolation is used when the robot needs to follow a circular arc. This is useful for things like drilling holes in a circle or welding a curved surface. The robot maintains a constant radius and orientation along the arc. Both are fundamental building blocks for more complex paths. For more intricate shapes, we use spline interpolation. This allows the robot to follow a smooth, curved path passing through several points, not just straight lines or arcs. Think of sculpting or complex machining. Splines provide flexibility and smooth transitions. Then there are hybrid control modes. These combine different techniques. Maybe the robot does a PTP move to a starting point, then follows a linear path, then a circular arc, and finally another PTP move. This gives maximum versatility for complex tasks. It's all about choosing the right tool for the job. And finally, reactive or adaptive path control. This is where the robot doesn't just follow a pre-programmed path. It uses sensors to see what's happening in the environment and adjusts its path on the fly. Imagine a robot navigating a cluttered warehouse or avoiding a person walking in front of it. This requires real-time sensing and decision-making. It's the most advanced form of path control, making robots truly autonomous and adaptable. Of course, it needs powerful sensors and algorithms. The choice of control mode always depends on the task: precision, speed, adaptability, cost. Now, let's talk about the spaces we control robots in. First, joint space. This is the robot's native language. It's defined by the angles of its joints, Q1, Q2, Q3, etc. Each point in joint space corresponds to a unique configuration of the robot. Controlling in joint space means directly commanding the joint angles. It's often simpler because the relationship between the command and the robot's movement is direct. However, it's less intuitive for tasks where the end-effector's position in the real world matters more than the joint angles themselves. Then there's Cartesian space, also known as task space. This is the world we live in. It's defined by the position, x, y, z, and orientation, roll, pitch, yaw, of the robot's end-effector. When we control in Cartesian space, we tell the robot where we want the end-effector to be and how we want it to be oriented. The robot's controller then has to figure out the corresponding joint angles. That's the tricky part, called inverse kinematics. Controlling in Cartesian space is much more intuitive for most tasks, like assembling a product or painting a surface. You care about the end-effector's position, not the internal joint angles. So, what's the goal of trajectory planning? It's to figure out the complete history of the end-effector's position, velocity, and acceleration over time as it moves from a starting point to an ending point, possibly passing through intermediate points called via points. Look at the diagram. It shows a path from S to G through points 1, 2, 3. The table compares representing these points in Cartesian space, x, y, versus joint space, theta 1, theta 2. Trajectory planning defines how the robot should move through these points in space, considering smoothness, speed, and constraints. This slide seems to be a placeholder or divider. Let's move on to the next topic. Just a quick note. This course is Introduction to Robotics, ARA 203, taught by Dr. Pasnes. Rajendra Kumar Arya at USR, GGSIP. Good to know the context. Here's a quick overview of the course structure. Unit 1 covers the fundamentals: what robots are, their history, types, key concepts like resolution, repeatability, accuracy, degrees of freedom, workspace, and the basics of end effectors and actuators. Unit 2 dives deep into kinematics, transformation matrices, forward and inverse kinematics, the Denevit-Hartenberg convention, and the Jacobian matrix. Unit 3 is dynamic analysis, forces, Lagrangian and Newtonian mechanics, equations of motion, and trajectory planning. Unit 4 covers robot programming languages and systems, including online and offline programming and typical applications. The listed textbooks are great resources for further study. Let's get into dynamic analysis of forces. We've seen how robots move, but now we need to understand why they move that way and what forces are involved. Look at the 2R robot again. We can ask questions like, how much torque does the motor need to apply to reach point Q? Can we make it faster? What if the path deviates from a straight line? To answer these, we need to analyze the forces and torques acting on the robot links. This is crucial for designing controllers and selecting appropriate motors. The second diagram shows trajectory tracking, where the robot must follow a desired path, which requires careful dynamic control. Robot dynamics is essentially the study of motion. Why does the robot move? How does it move? It's the science of motion, focusing on how forces and moments cause changes in position and orientation. In robotics, understanding dynamics is fundamental for designing controllers that can make the robot move accurately and efficiently. There are two main approaches to analyze this: the Euler-Lagrange method, which is energy-based, and Newton's method, which is based on force balance. Let's compare the two methods using a simple 1D system. On the left, the Lagrangian method. We define the Lagrangian L as the kinetic energy K minus the potential energy P. For a simple mass spring system, K equals 1/2 mv squared equals 1/2 m dot y squared, and P equals mgy. Applying the Lagrange equation d by dt of partial derivative of L with respect to dot y minus partial derivative of L with respect to y equals 0 gives us the equation of motion. On the right, Newton's method. We draw a free body diagram, identify forces like gravity mg and spring force kx, and apply Newton's second law sum of F equals ma, which gives us the same equation. Both get the job done, but Lagrange is often more powerful for complex systems. The Euler-Lagrange method is an energy-based approach. It's particularly powerful because it lets us derive the equations of motion without explicitly dealing with all the internal forces within the robot links. It's ideal for complex robotic manipulators. The core idea is the Lagrangian, L equals Ke minus Pe, the difference between kinetic energy and potential energy. The equations of motion come from the Lagrange equation shown. Newton's method, on the other hand, is more intuitive for simple systems. You draw a free body diagram, identify all external forces acting on the body, and then apply force balance equations like Newton's second law. The diagram shows a classic example: forces F, gravity mg, normal force N, and friction F. Let's apply the Lagrangian method to simple harmonic motion, like a mass on a spring. The Lagrangian is L equals T minus V, where T equals 1/2 mv squared equals 1/2 m dot x squared is the kinetic energy and V equals 1/2 kx squared is the potential energy stored in the spring. Plugging this into the Lagrange equation d by dt of partial derivative of L with respect to dot x minus partial derivative of L with respect to x equals 0, we get m double dot x plus kx equals 0. This is the familiar equation of motion for simple harmonic motion. The natural frequency omega squared equals k divided by m emerges naturally from the energy formulation. It's a neat demonstration of how the Lagrangian method works. Let's apply this to our 2R planar manipulator. We need to find the kinetic and potential energies. First, we need the positions of the centers of mass of the two links, M1 and M2, assuming they are point masses at the ends. The coordinates x1, y1 and x2, y2 are given by the equations shown, derived from the link lengths L1, L2 and joint angles θ1, θ2. These equations are crucial for calculating velocities and potential energy later. Now for the kinetic energy. Since the links are assumed to be rigid, their kinetic energy is purely translational. The total kinetic energy Ke is the sum of the kinetic energies of the two links. Ke equals 1/2 m1 times the square of x1 dot plus the square of y1 dot plus 1/2 m2 times the square of x2 dot plus the square of y2 dot. We need to find the velocities x1 dot, y1 dot, x2 dot, y2 dot by differentiating the position equations with respect to time. This involves using the chain rule and remembering that θ1 dot and θ2 dot are the joint velocities. Substituting these velocity expressions into the Ke formula gives us the final expression for kinetic energy. Notice how it depends on the squares of the joint velocities θ1 dot and θ2 dot, and their product θ1 dot times θ2 dot. Next, the potential energy. Assuming gravity acts downwards, the potential energy Pe is due to the height of the centers of mass. Pe égale m1 gi1 plus m2 gy2. Using the expressions for y1 and y2 from the previous slide, we substitute them here. Now we have both Ke and Pe. The Lagrangian L is simply their difference. L equals Ke minus Pe. The resulting expression for L is quite involved, containing terms with θ1 dot squared, θ2 dot squared, θ1 dot times θ2 dot, and trigonometric functions of θ1 and θ2. This Lagrangian fully describes the system's dynamics. Now we apply the Lagrange equation to find the joint torques τ1 and τ2. Let's start with τ1. We need to compute the partial derivatives of the Lagrangian L with respect to θ1 and its time derivative θ1 dot. The partial derivative of L with respect to θ1 dot is the generalized momentum associated with θ1. The partial derivative of L with respect to θ1 is the generalized force. The first term in the Lagrange equation involves the time derivative of the generalized momentum. The second term is the generalized force. Calculating these derivatives involves applying the product rule carefully, especially with the trigonometric terms. The results are shown here. Putting it all together for τ1, we take the time derivative of the first partial derivative of L with respect to θ1 dot, which involves differentiating terms like θ1 dot and θ2 dot, and subtract the second partial derivative of L with respect to θ1. The result is a complex equation involving the joint accelerations θ1 double dot, θ2 double dot, joint velocities θ1 dot, θ2 dot, and the robot's geometry and mass parameters. This is the equation of motion for joint 1. We do the same process for τ2, leading to the second equation of motion. Together, these two equations form the dynamic model of the 2R manipulator. They tell us the required torques to achieve any given joint accelerations and velocities. These equations can be written in matrix form. The terms involving the second derivatives of θ, θ1 double dot, θ2 double dot, form the inertia matrix M of θ. The terms involving the first derivatives, θ1 dot, θ2 dot, form the Coriolis and centrifugal terms, often grouped into a vector C of θ and θ dot. The terms involving gravity form the gravity vector G of θ. So, the dynamic equation becomes M of θ times θ double dot plus C of θ and θ dot plus G of θ equals τ. This compact form is very useful for control design. Notice how the inertia matrix M and the gravity vector G depend on the joint angles θ, while the Coriolis and centrifugal terms depend on both θ and θ dot. Calculating kinetic energy for a general robot involves both translational and rotational motion. The total kinetic energy K is the sum of the translational kinetic energy K translational and the rotational kinetic energy K rotational. For a rigid body, the translational kinetic energy is 1/2 mv squared, where m is the mass and v is the linear velocity of the center of mass. The rotational kinetic energy is 1/2 omega transpose I omega, where omega is the angular velocity vector and I is the inertia tensor of the body. We need to calculate these for each link of the robot. The inertia tensor 1 is a 3x3 matrix that describes how a rigid body resists rotation about its principal axes. Its components depend on the mass distribution of the body. The rotational kinetic energy is 1/2 omega transpose I omega. When calculating the total kinetic energy of a multi-link robot, we need to consider both the translational motion of each link's center of mass and its rotational motion. The inertia tensor I is crucial for the rotational part. It's calculated based on the geometry and mass distribution of the link. The diagram shows the components of the inertia tensor and how it relates to the moments of inertia Ixx, Iyy, Izz, and products of inertia Ixy, Ixz. For an n-link robot, the total kinetic energy is the sum of the kinetic energies of all n links. Each link's kinetic energy is the sum of its translational and rotational kinetic energy. The velocity of the center of mass of link I depends on the joint velocities and the robot's geometry. The angular velocity of link I depends on the joint velocities and the link's own geometry. The final expression for the total kinetic energy can be written in terms of the joint velocities q dot and the robot's configuration q. Often, it's expressed as 1/2 q dot transpose d of q dot, where d of q is the inertia matrix, a symmetric positive definite matrix that depends on the joint positions q. This matrix d of q is central to the dynamic equations of motion. Potential energy for an n-link robot. The primary source of potential energy in a robot manipulator is gravity. The potential energy of the entire system is the sum of the potential energies of each individual link. The potential energy of link I is mighi, where mi is the mass of the link, g is the acceleration due to gravity, and hi is the height of the link's center of mass above a reference level. So, the total potential energy P is the sum from I equals 1 to n of mighi. Calculating hi requires knowing the position of the center of mass of each link in the vertical direction, which depends on the joint angles q. The potential energy is a function of the robot's configuration q. Let's revisit the simple pendulum example. We found the Lagrangian L equals 1/2 ml squared theta dot squared minus mgl times 1 minus cosine theta. Applying the Lagrange equation d by dt of partial derivative of L with respect to theta dot minus partial derivative of L with respect to theta equals 0 gives us the equation of motion. L times theta double dot plus g times sine theta equals 0. This is the nonlinear equation for a pendulum. For small oscillations, we can approximate sine theta approximately equals theta. This simplifies the equation to theta double dot plus g over L times theta equals 0, which is the standard equation for simple harmonic motion. From this, we find the natural frequency omega squared equals g over L and the period t equals 2 pi times the square root of L over g. This confirms the Lagrangian method works even for nonlinear systems. Now for a double pendulum. Two masses m1 and m2 attached to rods of length L1 and L2. We need to find the equations of motion for small angle oscillations. First, the kinetic energy T. The velocity of mass m1 is v1 equals L1 times theta 1 dot. The velocity of mass m2 is more complex. v2 equals the square root of L1 squared times theta 1 dot squared plus L2 squared times theta 2 dot squared plus 2 times L1 times L2 times theta 1 dot times theta 2 dot times cosine of theta 2 minus theta. This comes from vector addition. The potential energy V is the sum of the potential energies of the two masses. V equals m1 times g times L1 times 1 minus cosine theta 1 plus m2 times g times L1 times 1 minus cosine theta 1 plus m2 times g times L2 times 1 minus cosine theta 2. For small angles, cosine theta approximately equals 1 minus theta squared over 2. This simplifies the potential energy to V approximately equals m1 times g times L1 times theta 1 squared over 2 plus m2 times g times L1 times theta 1 squared over 2 plus m2 times g times L2 times theta 2 squared over 2. With the simplified kinetic and potential energies, we construct the Lagrangian L equals T minus V. Then we apply the Lagrange equations for each generalized coordinate, theta 1 and theta 2. This involves calculating the partial derivatives of L with respect to theta 1 dot, theta 2, and theta 2 dot. After taking the time derivatives and substituting everything into the Lagrange equations, we get a system of two coupled second-order differential equations. These are the equations of motion for the double pendulum. They describe how the angles theta 1 and theta 2 evolve over time under the influence of gravity. Solving these equations analytically is difficult, but they are essential for numerical simulation and control. Here's a problem for you. A pendulum of mass m equals 1 kilogram is mounted on a moving cart of mass m equals 10 kilograms. The system has 2 degrees of freedom, the cart's position x and the pendulum's angle theta. Given the angle theta equals 30 degrees, angular velocity theta dot equals 1 radian per second, pendulum length L equals 0.5 meters, and cart velocity x dot equals 2 meters per second. Calculate the total kinetic energy of the system. You need to consider the kinetic energy of the cart, the kinetic energy of the pendulum's center of mass due to both the cart's motion and its own swing, and the rotational kinetic energy of the pendulum. Let's see if you can work it out. The solution involves breaking down the total kinetic energy into parts: the cart's kinetic energy, the pendulum's translational kinetic energy, and the pendulum's rotational kinetic energy. The pendulum's velocity is a combination of the cart's velocity and its own swinging velocity. The formula shown combines these contributions. Plugging in the given values, m equals 10 kilograms, m equals 1 kilogram, L equals 0.5 meters, x dot equals 2 meters per second, theta dot equals 1 radian per second, and theta equals 30 degrees, we calculate the total kinetic energy. The answer is approximately 22.475 joules. This demonstrates how to account for the combined motion of multiple bodies. Another problem. This time for an RP manipulator. Link 1 is rotary, link 2 is prismatic. We have masses m1 equals 2 kilograms, m2 equals 1 kilogram, lengths L1 equals 0.7 meters, L2 equals 0.3 meters. The center of mass of link 1 is at L1 equals 0.35 meters from the joint. The center of mass of link 2 is at distance d2 from the joint, and the end effector is at distance a equals 0.15 meters beyond the center of mass of link 2. Use the Lagrange formulation to derive the equations of motion. This requires careful consideration of the kinetic and potential energies of both links, considering their rotational and translational motions. The solution involves calculating the kinetic energy Ke and potential energy Pe for each link. The kinetic energy includes terms for the rotational energy of link 1, the rotational energy of link 2, and the translational energy of the center of mass of link 2. The potential energy is due to gravity acting on the centers of mass. The Lagrangian L equals Ke minus Pe is formed. Then, the partial derivatives of L with respect to the generalized coordinates theta 1, d2, their velocities, and the time derivatives of the generalized momenta are calculated. Finally, the Lagrange equations are applied to obtain the equations of motion for the RP manipulator. The final equation for tau 1 is shown here.